Hi everyone, my name's Gethin Rees. I'm from Arup and I'm here to talk about thermal mass and active slabs at the White Collar Factory. Um, the White Collar Factory is actually part of a wider development at Old Street Yard. So the site sits on the corner of Old Street and City Road, as you can see there on the left. And it's made up of predominantly of 6 buildings. So you've got the White Collar Factory, which is the large building there on the photo on the right. And another 5 buildings that surround it. So there's 3 low-rise office buildings. They're about 5 or 6 stories, and another 2 residential buildings. There's then a basement that runs underneath the entire site, connecting those buildings. So this presentation is going to concentrate on the White Collar Factory, which, as I say, is the tall one there. So the building is 16 floors of speculative office. We've got cafes at ground and roof terrace at the top. There's a running track at the top as well, which you may have seen knocking around the news when this got practical completion last year. So the floor plate is typically around 1,400 metres squared. That image on the left there gives you an idea of the sort of typical dimensions. And I just want to point out from the beginning that sustainability and the low energy has always really been at the forefront of the design of this building, both from the client, the design team, and through to the contractor through construction. And we're really proud that the building has achieved BREEAM Outstanding, LEED Platinum and EPC-A, which is kind of unheard of for a speculative office development in London of this size. And the use of concrete has really contributed to those accolades. So before this building was constructed, the White Collar Factory started as a conceptual project with the client in 2009. And the goal was to design an office building that not only was more pleasant for the users and the tenants, but also more energy efficient and crucially cheaper to build as well. So before the extensive use of air conditioning in the buildings as we have today, offices and factories typically had high ceilings, they had windows on both sides, and they had for natural ventilation, and they had a lot of exposed thermal mass. And this White Collar Factory idea really gave us a chance to sort of go back and question some of these ideas as to why have we ended up with these sealed glass offices that very much the norm at the moment. So through this work, we came up with some key characteristics that the White Collar Factory should have, and that's those at the top there. Generosity of volume, a robust construction, efficiency of system, flexibility of occupation. It should be people-centred and, importantly, adaptable as well to climate change in the future. And we mapped those key characteristics that we wanted to achieve, and that drew out 5 key principles of the White Collar Factory. So that's the building is deep plan, it's got tall ceilings, it's got a simple passive facade, it's got a concrete structure, and it's got smart services inside. So in this presentation, I'm going to concentrate on the concrete structure and the smart servicing. So that's the role of the concrete structure in the building and really how it forms a critical part of the smart servicing strategy for the office spaces. So that image there on the left is an image at the top of the building of 2 of the office floors. So you can see the exposed services and the exposed thermal mass. Before I get into the concrete, I just wanted to touch on this. I think one of the reasons why this building's been so successful is that those key principles I outlined earlier have really been embedded into the design, and at every stage, from the client, the design team and the construction, they've really been at the forefront. And in embracing these principles, it's meant that elements of the building have not been allowed to be treated as separate entities. So, for example, the facade has been very carefully designed so it lets just enough solar gain through so that the building systems can deal with it and provide cooling to the occupants. It provides just enough opening to allow natural ventilation to the spaces. And the concrete structure is another good example of this. Really, everything works harder in this building and does more than one job. So onto the concrete. It forms the superstructure of the building and the substructure. It also provides part of the external fabric of the building, as you can see on the left. It also provides the internal finishes of the building, and it provides the environmental conditioning to the space through activated thermal mass, and that's what I'm going to talk about now. So the use of exposed thermal mass is it's been touched upon already, and it's not new, and most people know how it works. We all know the feeling of being in a thermally massive building, and although it might be really hot outside, actually it feels very nice and comfortable in there. And one of the reasons for this is really well known. The thermal mass effect effectively acts like a sponge to absorb excess temperature. So you can see there on that graphic, the dotted, the dark blue line is the outside temperature. The dotted yellow line is the internal temperature of quite a lightweight building. So you can see it tracks quite closely to that outside building, outside conditions. And the light blue line is typical of what you might see in a very thermally massive building, where we're taking a lag in these temperature gains, and actually we're smoothing off the peaks and the troughs in the temperature, and that's the thermal mass really working hard there. But the other effect is probably a bit less well known, and it's called mean radiant temperature. So this is the reason why you might be, if you were sitting outside and it's 20 degrees C and it's a sunny day, you might be really warm. But similarly, you could be sitting outside, it's 20 degrees C and it's a cloudy day, and you might actually be quite cold. And this effect basically says that how we feel as humans is not just dependent on the air temperature, as a lot of people might think, but it's actually a combination of the air temperature and the temperature of all the surfaces around us. So we feel that radiant temperature of these surfaces around us, and that contributes to the temperature that we feel. So in a room like this, for example, this is a very lightweight construction. The floor is probably very roughly the same temperature as the air, and that's the temperature we're feeling. In a really heavyweight building, it's likely that these surfaces are a lot cooler, and that means that we actually feel that. And so for a given air temperature, we feel more comfortable. Or put another way, we can actually tolerate higher temperatures and still feel as comfortable when we have a lot of thermal mass in a building. So the idea at the White Collar Factory is to take these passive features that we've just been talking about of thermal mass, and to take them one step further and actually activate the structure. And what that means for us is actively cooling down the soffit of the office spaces. We call that concrete core cooling. So you can see there on that diagram, the cooling coming from the soffit surface of the office. So our aim was to activate a concrete soffit for a couple of reasons. So aesthetically, it meant we can clear the soffit of the typical mechanical cooling equipment that we might be used to seeing. You can see some of it there on the right-hand side. Another advantage of that, it means there's no moving parts to fail or maintain. So that's ongoing savings to the client and the building operator in terms of maintenance. And then on top of that as well, the system provides an energy efficient way of cooling the building, and it's very comfortable for the occupants as well. So that was the aim. And this is what it kind of looks like, really. That's a typical office floor of the White Collar Factory. You can see there are exposed surfaces at high level, but you can also see against this slide here, against all that stuff on the right hand side, there's a lot less going on up there, and you can really see the nice clean aesthetic of the concrete. And the added value of that is that there's a lot of area there that the people can see for that radiant effect. So in practice, how did we do this? So what it means, what we've done is we've embedded plastic pipework in the concrete soffit of the building. So these are laid out in zones, and they're spaced around about 150 millimeter centers. And we pass chilled water through these pipes. And what that's doing is it's basically taking that thermal mass effect that I showed you earlier and really magnifying it. So any heat that gets absorbed into that slab, we're purging it of that heat, taking it away, and really making sure that that slab can keep on absorbing heat throughout the day. In terms of the pipe work, it's a Rehal PE pipe. It's mostly about 20 millimeters in diameter. We try as much as we can to lay it without any joints. It's continuous loops in the concrete. But where we do need joints, I think it's brass. It's a brass push fit coupling system that also gets embedded within the slab. So this is just a typical section of the slab. So it's a 350mm in situ concrete slab, and you can just about see those blue circles at the bottom, which represent the rehoused pipework. Now they're tied to the bottom layer of reinforcement before the concrete's poured. So they're roughly around about 45mm from the underside or the bottom of the soffit, depending which way you're looking at it. And these are just a few pictures of the pipework installed on that rebar before the concrete's poured. So you can see on the bottom right image there how the pipework's effectively clipped to that bottom layer of reinforcement. And then simply the concrete's poured on top, and that's it. It's in, so you've got to hope that there's no problems with it. I just wanted to touch on this. So the different loops, they're sort of they form different control zones across the office soffit, and to control those we need a number of valves, and the team worked really hard actually to, as well as casting in the pipework, we also casted in these control valves within boxes in the slab. So really, again, working really hard to ensure a clear soffit and getting that really nice aesthetic. So what does the result look like? So you can see the image on the right there. That's a thermographic image of the slab, the same piece of slab that's on the left. And you can really see the coof effectively being radiated from those pipes onto the slab, cooling that surface down. And that's really providing that cooling and radiant cooling effect that I described at the start. And I just wanted to close on this slide, which really just demonstrates how effective the system can be. It's a bit geeky, so I'll just talk through it for just 2 minutes. We're still in the process of testing and analysing the system finally, but this was the results of a test that we did in September last year. So the red line shows the room air temperature. It's for a given zone in level 11. The blue line shows the temperature of the slab, the soffit in that same zone. And what you can see there is on the first day on the left, the concrete core cooling system was off, and you can see that as the sun comes out around 1 or 2 p.m, you can see the space temperature start to rise. It goes from around 24 degrees up to 25, 26 degrees. As we'd expect, as the load comes into the space. Correspondingly, the soffit temperature also rises up from about 21.5 to about 22.5 degrees. The next day, the one in the middle, we've actually turned the concrete core cooling on. So you can see almost from the moment that is turned on, you can see the blue line, the slab temperature starts to drop towards the set point, which is about 19.5 degrees, which is what we're trying to achieve there. And correspondingly, you can see the room air temperature, which is the red line at the top, starts to fall as well, and it starts to fall quite quickly actually into that target space temperature that we're looking for. So even on that day when the sun starts to come out at around, again, 2 o'clock, you can see the space temperature starts to rise slightly as the load comes into the space, and the slab temperature starts to rise slightly as well because it can't deal with all that heat at once. But you can see from that top bit there that the system actually works very well at keeping the space temperature within the target zone, which really just demonstrates how effective these sort of passive systems can be when they're employed properly. So I just wanted to leave on that. So thank you for listening.